So first things first, before we even try to sort of change the structure of this graph, the first thing that we probably should do over here is try and get an estimate of how much I can potentially improve it, right? Is there an iteration period bound that I need to be concerned about in the first place, right? Because right now I have seen that my critical path is 5 time units. I was thinking of reducing it to 4 so that I can get a 100% hardware utilization efficiency, possibly, right? Because as long as n is equal to 5, it always means that even if I reduce to 1 multiplier and 1 adder, I can get at best 80% hardware utilization, right? Because there are only 4 additions and 4 multiplications, right? So the first question to ask is, can I bring n down to 4? In other words, can the critical path be reduced from 5 to 4? Okay. Before we straight away try to go about reducing the critical path, one thing that we can sort of try and answer over here is, is there a fundamental bound on the critical path, and how would you go about finding that? Is there any lower limit that you can sort of think of for this graph on how low the critical path can potentially be made? What is that number? Can I reduce the critical path to 1 multiplier, or is there anything else in the graph, in the structure of the graph, that prevents me from bringing it even that low? What is that? It's a cycle in the graph. What do cycles imply? Iteration period bound. Okay. So there are 2 cycles in this graph. Iteration period bound is going to be max of 1 plus 1 plus 2 by 1, which is basically for the inner loop, right? 1 adder, another adder, and 1 multiplier, and 1 delay element. Whereas for the outer loop it becomes 1 plus 1 plus 2, again 2 adders and 1 multiplier, but this time divided by 2 delay units, that is 4. So this is one thing that you can straight away do. The moment that you have a system, probably the first thing that you should look at is say, okay, given this kind of hardware that I had, capabilities that I have, is there a limit on how low I can bring the critical path? And although critical path and iteration period are not the same thing, because after all I could have 2 parallel copies running, the moment I have a loop with a single delay element on it, it means that I can't even use parallelism, right? Even if I try parallelizing, there is a fundamental dependency between one iteration and the next one, which means that the critical path, the best critical path that I can achieve is basically going to be given by whatever is the limitation within one loop. So now what it looks like is my iteration period bound is 4, and I do have a loop that has only 1 delay element on it, which means that as far as that loop is concerned, I will never be able to bring the critical path down below 4 time units. So okay, 4 is a reasonable value to target, okay, and it just so happens that if I can get n equal to 4 and then achieve the rest of the implementation using 1 adder and 1 multiplier, that's great, because I would actually hit 100% hardware utilization, okay. It's a coincidence in this case, because the n equal to 4 and the fact that there are 4 multiplications and 4 additions is just incidental. There was no requirement that it should automatically be the case, okay. Alright, so now that I have a target, I want to make my critical path equal to 4. What can I do about it? How do I achieve that critical path equal to 4? I can do some kind of retiming or pipelining, okay. Just to clarify, I am using the words retiming or pipelining. Pipelining is in some sense a special case of retiming, okay. The reason why I say it separately is pipelining is sometimes easier to visualize. It's easier to sort of see where I can do pipelining. For example, I can fairly easily see that this is a potential cut set for pipelining, and if I do pipeline along that cut set, that actually straight away achieves my objective, which is that my critical path has reduced to 4. So let's see how that helps us. After I have done that, basically what I can say is, I put delays over here. What does my directed acyclic graph now look like? Or my, the directed acyclic graph is ultimately what I am interested in for my scheduling, right. So what it would look like after I have done this magenta cut set is, now operation 4 also does not have any dependencies, okay. So all the others remain the same. So 5, 6, let me just make this 7, 6 and 8 remain as before, okay. The output of 5 and 7 are used by 3, the output of 3 is used by 1, but the output of 1 is not used by 2 in the same iteration. So that edge has been broken as far as this scheduling is concerned. I do not need to draw an edge from 1 to 2, okay. The outputs of 6 and 8 are not being used in this iteration, they are going into delay elements, okay. And what I have then is, I have 4 whose output is then used by 2. Now this is actually very interesting, right. I have now got a potential implementation where if I look only at the adders, I have achieved my target. So two things have been achieved over here. One is that the n that I want has now become equal to 4, and the number of adders has also become equal to 1, right, or can be made equal to 1 if I am able to keep the schedule like this, that is 4 and 2 over here and 3 and 1 over here. Since there are no dependencies, there is nothing preventing me from keeping it like this, right. So the maximum number of additions. So I mean, one thing to keep in mind, operation 4 and operation 2 actually have some mobility. In other words, operation 4 could have been scheduled in step 1 or step 2 also, and operation 2 could have been scheduled in step 2 or step 3. So they have a mobility of 2 time units, right. But if I push them later, then I end up needing 2 adders in step 2 or in step 3 or in both. But if I sort of keep them as early as possible, then I can finish operation 4 and operation 2, and 3 and 1 can then be done in steps 2 and 3, okay. So the number of adders, in other words, can be made equal to 1. What about multipliers? I could have pushed these 2 down, right, because there are no other dependencies after that, but I can't push these. So the number of multipliers, I need at least 2, okay. So I have got closer to my target, right, but not quite achieved the final goal that I wanted, okay. What can I do about that? How do I now further break this and improve upon it? So you see the procedure that I am following, right. I mean, I essentially started off with a critical path of 5 time units, right. Obviously that was more than required. I know that there is a fairly straightforward way by which I can bring it down to 4 time units, and the shorter the better in general, okay. So once I have brought it down to 4 time units, I can then sort of think of what is the best possible hardware allocation that I can get away with, right. In this case, the reduction of critical path to 4 time units was easy. I just applied a pipelining along that magenta line over there, the dashed line, okay. That achieved that purpose at least. Yeah, so that's a good point. See, generally speaking, the goal of pipelining, or rather the rule of thumb that is used for pipelining is, if I have a long chain, then pipeline in such a way that I am able to break that chain into equal sized parts, so that the overall critical path reduces, right. In this case, that is not really what I am concerned about, because I know that my critical path can only come down to 4. So then I do not really need to worry about balancing the different parts of the pipeline. Over here, my only goal in pipelining was to reduce critical path to 4 and break some dependencies so that some operations can be moved around. Okay. So if I take that as my target, then I don't really need to worry about between node 3 and can you pipeline there? So the question is basically, is this a valid pipelining cut set? And it's not, right? Because there is this edge over here and this one over here and this one over here are in opposite directions. So this is not a valid pipelining cut set, right? So that's why I said you have to be careful about pipelining versus retiming. Pipelining is applicable only in the places that are feed forward. Okay, and the magenta line that I have drawn over here, all the edges are going from left to right. So that cut set that I have drawn over there, everything is going from left to right. I can safely pipeline. Just put a bunch of registers over there. The output gets delayed by 1 cycle. Everything, all paths have been delayed by 1 cycle. But if I try doing it on this orange line, it actually causes problems. Okay, so you have to be careful where you apply the pipelining. That's actually the most important thing in all of how you apply this process. So now, where have we landed up, right? We can see that the fact that both 5 and 7 are feeding into 3, right, and the result of that is then being used by 1 means that 531, 731 are both critical paths. As long as they remain that way, 5 and 7 both have to be scheduled in step 0. So I have to be able to break one of them. I have to be able to break one of those dependencies. But both of them are feedback loops, right? So it doesn't look obvious that I can do any pipelining over there. Or to be more precise, I cannot do any pipelining over there. But what can I do instead? I can retime, okay?